I know nitrogen gives you 5, right? And there's 3 of it, giving you a total of 15, right? And then negatively charged was actually 16. Okay? And then I just fill it in. Whatever I have left. Well, I used 2 single bonds already, which means that I use 4 electrons. Alright? I have 12 left, and so I can fill it in. I'll give this one 2, this one 2, and this one 2. Okay. So that's one structure. I use up all my electrons. I try to fill them in as evenly as possible. All right? And now I see I can flow electrons to give me a different structure. Now, if you look at this, the nitrogen in the center, if you do the trick, you will see that it has 6 electrons, 1 more electron than the 5 it's supposed to have. So that would be the -1 charge. Right? And it works because everything else is neutral if you just do the trick. So that works. That's valid. So what you would do next is see if you can flow electrons into any other atom. And if you're looking at the 2 outside nitrogens, they're both electron efficient, right? Because they both only have 6 electrons instead of the ideal 8. And what you can do is that since you have a nitrogen in the center with 2 lone pairs that's negatively charged, it can donate electrons into the 2 outside nitrogens. Alright? So I'll show it like this. This is going to form a pi bond with the adjacent nitrogen. Like so. The lone pair becomes a pi bond now. To have it form a charge of this, I find out that it's going to be 6, so it's going to be -1. And the total charge of this molecule correlates to the initial structure given, so it's fine. I also see that the nitrogen, the same center nitrogen, it has a lone pair, and the one on the left is still electron efficient, so I can maybe donate electrons into that nitrogen now. Like that. Okay? So now I have a double bond here. Okay. And now I calculate the charges. I find that the center one is going to be a positively charged. 2 on the outside is going to be negative. And then I sum up the charges, and they equal to -1, which works. All right? And now I have to calculate the hybridization of each nitrogen. Okay? The center nitrogen, looking at the lowest, the one with the most pi bonds, center nitrogen is going to be here. This one has 2 pi bonds with the 2 lone pairs that are participating in the pi bonds, so it's going to be sp, the center one. Now the outside ones, none of the lone pairs are participating in resonance, so you can count that as part of the hybridization. So you count 1, 2 lone pairs and 1 sigma bond, that would make it sp2. All right?
Can you explain the center one again?
Okay, the center one?
Yeah.
It's just like the oxygen, right? Where you would count sigma.
Never mind, I see it. The 2.
You see it, right?
Once I got it.
You count the lone pairs only if it's not participating in resonance. Well, in a double bond, right? This is just how we draw it, but these two bonds are not equal. One is a sigma bond, and one is a pi bond, all right? So you have two lone pairs and a sigma bond. But see, the resonance that I have here is not on the resonance structures of this. So when I said it was sp2, it actually isn't, because there's another resonance to give a lower hybridization of the nitrogen. So I'll show you guys what that is now. So I have a lone pair here. This nitrogen is positively charged, electron deficient. I can flow it into it. But with one of these lone pairs, it doesn't matter because they're symmetrical. I would go like that. And this lone pair, this pi bond is going to go back to that nitrogen. When I do that, I get this structure, right? The center nitrogen is still sp, positively charged. The terminal one on the right side is now negatively charged with one sigma bond. And the one on the far left is going to have a triple bond, which means that this nitrogen actually only has one lone pair that's not participating in resonance and one sigma bond, which makes it sp, which makes every nitrogen in this compound sp. Because you do the same thing with another nitrogen. Okay?
I don't understand.
Does it have to be the same for every nitrogen, or like every middle nitrogen and every?
What do you mean?
Why do you say that? I know that one just happens to be sp, but why does that have to be sp if the central one's sp?
It doesn't have to be.
It doesn't have to be, right?
It doesn't have to be.
Okay.
I'm saying the lone pairs that are participating in resonance, you can't count those as part of your hybridization, right?
Yeah.
And when I didn't have this structure, I would think that it's actually sp2 because these two lone pairs haven't participated at all.
So you had another.
But then I have another one that I realized, oh crap, right?
Yeah.
This lone pair can flow into here, pushing the pi bond of these two nitrogens into the far right, making it to a lone pair. So, which means that if I have this structure, two of the lone pairs of the nitrogen will be two of the nitrogens, two lone pairs will participate in resonance, giving it sp hybridization.
But isn't that a double bond?
Where?
The second two nitrogens, like your fourth resonance structure. Between the second two nitrogens, shouldn't that be a double bond?
No. The double bond flowed out. Remember, I showed it here.
Oh, you flowed that one.
See that one? Now I have two lone pairs on this nitrogen, right? But because I pushed a lone pair from the far right into the center one, I have to push this one out because nitrogen can't disobey the octet rule.
Yeah,
if I leave it there, it will have 5 bonds, giving it 10 electrons, and that's not good. So the only way I can do that is by pushing that pi bond out, making it into a lone pair of nitrogen. Okay?
Does that need to be a -2 on the and on the that?
Yeah, it's negative 2. I apologize for that. Yeah, negative 2.
So for all the resonance structures, for the S3, the second one on top, would all the nitrogens have octets? I can't see it.
This one? No, it's not octet split. You have a single bond, and then you have 2 lone pairs, right?
Yeah.
2, 4, 6 only. This is just going back to the initial structure that I drew.
Oh, okay. So
Okay.
is that a resonance? We put that on the test, and that counts resonance?
It's a resonance, but it wouldn't be a major contributor,
Because it doesn't have the octet, right?
Yeah, it doesn't have an octet. So the first thing you use for finding out which is the most stable structure is the octet rule, right? And you want to maximize bonding. You want to put the charge on the negative on the most electronegative atom, and the positive on the least electronegative atom, right? And then you want to minimize charge separation. Those are the 4 rules you have to abide by when you're talking about resonance and stability.
So since they only ask for resonance structures, that would count.
Yeah, it will count.
Okay.
But if you ask for a major, you have to determine which one's the major structure, right?
Okay.
So between these 4, I know that the first 2 the far left nitrogen doesn't have an octet, whereas compared to the last two, every nitrogen has an octet.
Yeah.
So I can kind of cancel that out of the way. And now I'm looking at these two, right? So I'm looking at these two structures, and I have to determine which one's the major contributor. Well, I go out the rule, the second rule, which is maximizing the number of bonds, and the last two structures, pretty much have the exact same number of bonds, so I can't use that. So I have to use the third rule, charge, the charge of the most electronegative atom, right? And I look at this, and I see that, well, I have a -2 on one nitrogen, and then I have a negative on two nitrogens. I guess, can't really tell, but the thing is, if you think about it, a -2 charge is a lot higher energy than a -1 charge, okay? Even though you have two of them, this is really high in energy, so this would be a major contributor as opposed to this one. Alright? Because the more electrons you push into a system, the repulsive force is going to start acting on it.
Can we count the hybridization for the major resonance forms? Or minor and major?
All of them in consideration. The ones that, you have to look at the lone pairs that are participating in resonance.
So that's what hybridization is, nitrogen on the left. And you'd say that's P because of even the minor one is included.
Yeah, it has to hybridize in order to have that, because remember, the more resonance structures it has, the more stable it is. So it's gonna want to have more resonance, and it's gonna want to use lone pairs to resonate. To resonate. Right?
Sorry. Repeat what you said 1 to 4 was when we're looking at resonance, the rules.
Okay. Well, the table is on in your book, but I'll give it to you right now. So first rule is octet. Right? Second rule is maximize bonds. Third rule is charges. So negative on more electronegative. And then the fourth rule is you minimize charge separation. Alright, those are the 4 rules for determining the major contributors. And we just go down the list.